Thank you, and thank you first very much to the organizer for inviting me here. So I would like to report on this work with Pablo Cubides on definability of Berkovich curves. So the main point would be actually to make a precise relationship, say as precise as possible, between two variants of the same object. So say first maybe the Berkovich version of non-archimedean analytic curves. And also, since we are here in a conference about model theory and visual fields, a model-theoretic version of the same object, so by which I refer to the work of Hrushovski and Loeser. So I think it's quite clear for everybody who's been working the topic that they're pretty much the same objects. But we would like somehow to understand better how you can pass from one to the other, what the one point of view tell you about the other and the other way around. For instance, maybe the first question that comes to mind is, in this model-theoretic version, of course, you have a notion of definable set. So what are these definable sets in the Berkovich setting? So we are used to thinking about Berkovich curves with some precise structure, basically coming from the semistable reduction theorem. I will recall a few things about it later. So this would be a first question, and you could also try to go the other way around. Like there are some tools we use in the Berkovich setting, something we like residue curves and reduction maps and so on. Can you say something about them? Can you define them, for instance, in the model theoretical setting? So that's the kind of thing I want to do. So first, introduction. So let me just recall a few things about both settings. I will try not to be too long, but probably it's important to say a few words about each of these settings in order to be clear on what I'm talking about. So Berkovich spaces. So here I fix some field K with an absolute value. So my field, my base field, will always be denoted by small k. So it's complete, non-archimedean, and it will, for me, it will also be algebraically closed. Okay, and maybe most importantly here, this is an absolute value. So this is really an evaluation of rank 1. And for all we do in Berkovich geometry, it's important to be of rank 1 here. At some point, I will need to assume that too. Right. Yeah. Yeah, OK. Actually, I want to have some setting that works for everything, model theory and so on. So here for the Berkovich space, I could remove algebraically closed. I could remove non-trivial. But when I want to do something, OK, in both settings, it's better to have like all those hypotheses. So let's fix this to be safe. Thank you. Well, so now what is the definition, say, of the affine space? So let n be some non-negative integer. The Berkovich affine analytic space of dimension n is, so I will denote it like this. I mean, the notation is Berkovich notation, of course. So A, n, and here analytic. it's as a set, it's a set of say multiplicative seminorms on the ring of polynomial over K with n variables that induce the given absolute value, the one I started with, on my base field K. Okay, so multiplicative seminorm, you should think of it like basically like an absolute value, except you allow to have some kernel. Of course, there is much more to the definition. Here, I just define a set. It's of course a topological space and even a locally weak space and so on. But for today, I'm only interested in this set. And okay, good. And now let me take a point, say x, in this analytic space. I can associate to it some residue field. So the associated absolute value of seminorm, multiplicative seminorm, I like to denote it like this, just to remember it's somehow a multiplicative seminorm. And I can define P of x to be, say, the kernel of this seminorm, meaning like the set of polynomials that take such that if you apply the seminorm, you find 0. So this is a prime ideal, basically because you required it to be multiplicative. And then so you can look at your ring here. The quotient is a domain. So you take the fraction field, and this is a field. And of course, the multiplicative seminorm you started with has no kernel anymore here. You just killed it. So you find an absolute value. And so you can complete with respect to the induced absolute value. And you find now a complete valued field of rank 1, etc. So to each point, you associate such a field here. And of course, you can also, once you have this field seen as a valued field, you can recover the seminorm you started with just by evaluating the polynomials. I mean, the polynomials obviously map to this field here, so you can recover your absolute value, your seminorm, if you want. It's also a way to say that from Berkovich point, you find like you associate some canonical valued field, so which tells you that in more model-theoretic terms that you can associate some type that need not be realized over K, of course, but that will be over some bigger field. Okay. So you could think as this Berkovich space as a space of some types. And I want to be more precise. So in what follows, I will restrict to curves. So let me also give the example of the line before going to arbitrary curves. And here I can be more precise about the points. So if I want to describe the points, I will look at the associated valued field, this curly h of x that we call the residue field. And there are two invariants I would like to consider. First, I can take the residue field, which I denote by the twiddle of this residue field, and mod out by the residue field of the base field, and look at this, sorry, look at the, no, I don't mod out anything, of course. Just look at the transcendence degree over the residue field of the base field of this one. Okay, first thing I want to consider. Second, I can look at the value group, or maybe it's divisible closure, and mod out by the value group of the base field, which is already divisible because it's algebraically closed. Oh, sure. Okay, yeah, let me just leave it like this. Like, probably you know this invariant very well, so. Here you cannot read?
What do you call what did you write at the very end of the last, what is the notation?
It's a curly H. Here?
Curly H.
Yeah, something like this. Okay, so that's my notation for the residue field. I'm only going to use it here. Yeah, maybe not. So transcendence degree and dimension of the relative dimension of the value group, and then so these are like the two invariants that you find in Abbiancar's inequality. So you know that the sum of those two is at most 1. So there are a few possibilities, basically 0, 0, 1, 0. 0, 1. Okay? And Berkovich defines the classification of the points according to these possibilities. So actually the first one you refine into two kinds. So first here x could be, so my curly h of x could be the base field k itself. So this is called type 1. It's just like the usual points of the field, of the base field, and otherwise it's called type 4. And since those two are 0, it means that curly h of x is a non-trivial immediate extension of the field k. Okay, here. So I have a non-trivial transcendence degree, meaning 1. And this is called type 2. And we have actually an explicit description of those. It necessarily corresponds to the sup norm on some disk, say with center closed disk with center A in the base field, radius r, with r inside the value group. And type 3, that's what remains here. And it corresponds to the same kind of thing. So a sup norm on a ball, which here in this non-Archimedean setting is multiplicative. And same condition except for the last one, where since you want something non-trivial to happen on the value group, you require the radius not to belong to the value group. Okay? And so that's Berkovich classification for points, which would work. So it's I only used here the Abbiancar inequality, so this would also work for curves, for instance. And I will use it later. And once you have this in mind, so basically like you know all the points, so k points and points associated to balls. This one, okay, maybe not too much, but let's forget about that at the moment. And you can make a few pictures. So of course this, like you have kind of a continuous families of those points. So yeah, my notation for this point here, associated I will think of it about like generic points associated to the disk of center A radius r, hence my notation eta as like usual for generic points in algebraic geometry with A and R. And so you have, when you let R vary, you have a whole family of them. For instance, if you start with a point 0 in your space, you can draw a line starting from here, and maybe you have the point eta 0, 1, like the so-called Gauss point, corresponding to the norm, the sup norm of the disk with center 0, radius 1. And okay, you could go higher and higher, center 0, radius 2, and so on, towards infinity. And if you start with another point here, say the point 1, for instance, what happens? Of course, you understand that this 0 here is not well defined, like the center of the disk of center 0 and radius 1. You could pick it out at 1 if you wanted to. And so this point is also the point with center 1. So the line I should draw from this point 1 meets the one I just drew here, precisely at this point. And you can play this game starting from every point in the base field. And when you do that, you find this familiar picture of a tree, or maybe a real tree, with many, many branch points in some kind of dense subset of this line. Okay, so that's my usual picture, and which tells you, by the way, like this affine Berkovich line is arcwise connected and locally arcwise connected, and this is probability that also holds for more general varieties in arbitrary dimension. Okay, very good. And so this is my picture of the line, and there are some spaces that will be useful later. So a disk looks very much like a line, except that just cut at some point, of course. So disk, say the disk of center 0, radius 1, or maybe the open disk of center 0, radius 1, open Berkovich disk looks something like this. So I have point 0 here, and okay, it's a branch, like just one branch like that, and it's okay, it's some contractible space, and actually you would like to, it wants to be contracted on this point here. So if you happen to have a disk branch onto a point, you could contract to the point at the boundary. And another interesting space to consider is an annulus. So an annulus, how do you build an annulus? You start with a disk and you remove a disk. So I would remove like some part, say, below this one. So it looks like this. You have some kind of distinguished segment inside this, and then all the remaining branches that I didn't touch. And there is something specific in this picture, that this interval here is something, maybe I should choose another color. Okay, put this red. This is something well defined, and this is called like it's called the skeleton of the annulus. And if you sort of understood what I draw just on the left, you understand that the annulus retracts onto this skeleton in quite a natural way. Okay. Oh, thank you. Uh-huh. No, other one? Yes. Okay, so now part B should be the model-theoretic version. So Hrushovski Loeser's spaces. And I'm going to be very brief on them. But say if you start with some V, say some algebraic variety over, say my field is all K. So they associate a space that they denote by V hat, which is a space of something definable, stably dominated types, concentrated on V. Okay, and well, they prove several deep results about this object. So in quite a wide generality, so basically algebraic, or for something you would need a quasi-projective. And one of the first things they prove is that, so it's not exactly a definable set, but it is and canonically so. Canonically. Strict pro-definable set. So pro-definable, you can guess you have a projective system with definable maps, and strict means that at some point the maps in your system become surjective. Okay, and in the case of curve, which is why what I will be interested in now, if V is a curve, of course you have more tools to investigate your space, and they prove that that is actually not only pro-definable, but in some sense definable, or more precisely iso-definable, which means that so your map in your projective system become bijections at some point. So yeah, kind of yeah, something definable anyway, which is a nice consequence of Riemann-Rohr theorem, which okay, I don't have so much time to tell you, but nice. So what you should understand here is like the proof of definability of curves is actually far from direct. You first need this pro-definability. I mean, it's really a consequence on this pro-definability plus Riemann-Rohr, which tells you something else, like iso infinity definability technically, which has this as a result. And okay, so what I will explain here is also how to get a more direct way to define curves, and in fact how to do it with having in mind the geometric picture of the Berkovich curves. But before doing that, let's make precise the relation in the case of the line. So A1 hat, so like the space of just written here, stably dominated type. So in this setting, stably dominated is same as orthogonal to gamma, to the value group. So it tells you that you cannot increase the value group, and which means that of course you need to be definable too, which means that in my picture here I need to remove the type 4 points and the type 3 points. So all that remains is the type 1. Okay, so say the type 1 and 2 points. It's not definable. Yeah, not definable. Basically, I mean, if you certainly understand Berkovich thing, and you know that you need to use like this infinite family of disks to define them, and okay, basically something like that happening. So what you have here, it's only the type 1 and 2 points, and this form a definable family. So it's just like okay, like so just a set of balls. I can write that down. It's just a set of balls. Okay, they don't. But in this case, you see that if you yeah, if you go out rank 1, basically you add something to the value group in this situation, and they would not be stably dominated. Okay, so no, you don't. No, I mean here it's no. This is true. Yes. So you have the set of balls. So with centers in K and radii in the value group. Yeah, maybe the value group. Okay. Okay, so maybe this is not exactly a definable set. I mean, it depends where you want to define it. Like if you want to use the valued field and its value group. So basically, you have to do quotient because there are some balls that need to be identified. But okay, it's a set we understand quite nice by some quotient if you want. And okay, I add the corresponding sort to the set of 4 balls, and we were good here. Okay. Okay, so I don't want to say much more about that, but of course, I mean, the story goes much further here. And what they managed to get is to have a very general result for quasi-projective variety of strong deformation retraction of this V hat onto a space that's close to this kind of skeleton. That's technically some gamma interloop space that you define only using the value group, and they retract that on it. And they also have consequences for the associated Berkovich spaces that in this case they also have the homotopy type of some C finite CW complex and so on. Okay. Right, yeah, algebraic and quasi-projective, that's for sure. Yes. No, yeah, I was just mentioning it, but of course, you're right. So second, I would like to be a little more precise and about semistable reduction, meaning being more precise about how we see Berkovich curves and how we think about the structures as analytic spaces in a geometric way. Semistable reduction. So let's first pick X, be say smooth, projective curve over my base field, okay? And let X note maybe be a semistable model. So over the ring of integers of this one. And okay, and let I look at its special fibers, so which I'll denote by a twiddle, which is just to start with your model and you tensor with the residue field. So semistable model, you don't care too much about what it means. Like basically, it tells you that the special fiber is a reduced strict normal crossing divisor. So it looks like something like you have really mild singularities. So basically, you have only in this special fiber, you only have smooth points and maybe also a few double points, but quite nice. So that meet like transversally and maybe something like that. Curves are allowed to have some self-intersection, and that like basically the most bizarre thing you would do. Okay, and maybe I add another component here. That all the irreducible components of my space. Okay, and now okay, I want to draw a picture here and okay, and tell you something here. Maybe I also add something for the generic points of my components. 1, 2, 3, fourth one here. Okay, I'm gonna put them all on the same side. And let me label these generic points. 1, 2, 3, 0, okay. And now I can tell you, I won't prove it, but something we know, how to pass from this reduction to the Berkovich analytification of this curve. Okay, so here I will draw a picture of this analytification. And actually we have a map that goes in this direction. That's a reduction map. And we know what are the preimages of the different points on the left. So if you take a generic point, let me put twiddles on these because they are on the special fiber. This is a single. We know that the preimage of the generic point is a single point that I denote with the same letter, but just removing the twiddle. So I have 4 of them. Let's see, like this. So x0, x1, x2, x3. Okay. And also you have many smooth points. And we know that the preimage of a smooth point is an open disk. Okay. An open disk. So let me draw that in blue. So for instance, this smooth point here will correspond to some open disk. And the boundary of the open disk, as you can expect, is going to be the point associated to this generic point. So I draw a disk here that correspond to this smooth point. And I have many smooth points all over the place that all branch onto the same one. Okay, good. And I could do the same for all the smooth points. And now, if I look at double points, the preimage is an open annulus. So exactly the picture I draw there. And then you have so for instance, this point. And you see that I have this skeleton here with two ends, and the two ends are going to go to the two generic points associated to the double point. So here it's the component, irreducible component 2 meeting the irreducible component 0. So this one will correspond to an annulus here. Okay, so that's just the skeleton of my annulus. Maybe I can branch some disk here if I like. Very good. Okay, if you want the picture to be complete, you should add a point, say this one that's between 3 and 0, here. A point between 3 and 1, here. Also some kind of annulus. A point between 1 and 2. And finally, this double point here is something like a point between 3 and 3. So it's just like an annulus that you just glue onto itself like this. So just a loop inside the graph. So that's what my graph, my Berkovich space looks like. And you can branch disk everywhere. I don't draw that too much because as you see, they don't give much about the topology. You can, the first thing we want to do is to retract them onto the boundary point. And so the outcome is that the homotopy type of this curve is exactly the homotopy type of the dual graph of this reduction. Okay. Of course, what I said here, it said that you can retract actually your space onto this skeleton, this graph I drew here. That would be the skeleton of my curve, and the skeleton is like the analog of the gamma internal set I just mentioned in Hrushovski and Loeser's work. Okay. So all of this is to tell you that we have quite a nice understanding of the structure of Berkovich curves thanks to the semistable reduction theorem. And so my point here is how could we use that to get a better grasp on definability on Berkovich curves? Could we somehow use this? So let me skip this and go to, maybe go to my last part, which should be how to go from semistable models to definable sets. Okay. So I will keep in mind, we will keep in mind the picture upstairs. And in this setting, we have this set x0 to x3, which I will denote by S, which is something that we call, it's some kind of definition, if you want, a triangulation. Triangulation meaning that the complement is a disjoint union of disks, open disks, and open annuli. And disk and analy we understand. So plus this finite set. So basically you understand all the curve once you have a triangulation. Okay. Sorry? Actually, yes. Finitely many annuli. You're right. This is also important. Finitely many annuli. That comes exactly from the finitely many double points in your semistable model. Yes, and so we could, so disk and annuli, we know how to define them. So I gave you the definable version of A1, this A1 hat. You just keep just a set of balls, and we agree that we can define set of balls. Okay, so like what would be the first attempt to give a definable structure on X an, or maybe actually I will only restrict to the points of type 1 and 2 because it's what makes sense in this model theoretical setting. So we would like to write that, and okay, maybe I restrict later. Sorry. This curve is so you can write it as a disjoint union of. So we have the finitely many annuli, so say the AI, and disjoint union of we have the set, the triangulation S, and we also have a disjoint union of disks, dj. So I hope this is clear that these are annuli and these are disks. And so this union is finite. This one is infinite. Okay, so it's not so good, of course, because you don't want infinite disjoint union to have something definable. So this is fine, this is fine, this is not. So which means that you should find a way to put somehow like all these disks by like to group them in finitely many groups to end up with something definable. Okay, and where does this come from? Of course, it's clear how you want to do it. All the disks that remain here, they are just they have the. You want to group them according to which point is at their boundary. So you have infinitely many disks with endpoint x1, infinitely many disks with endpoint x2, and so on. So let's have a closer look at what happens around a point. So around a point xi. So one around the point of the triangulation, so to speak. So the picture is like this. So we have xi, and we have maybe some distinguished direction that are the direction of the skeleton that we don't want to consider. And all these disks that we want to consider now that I just do in blue. Okay. And what I'm really interested in is defining this set, this WX, if you want, that is a union of all the open disks here. Yeah. So WX is a union of open disks, and maybe and also the point xi. If you wanted the pre-image of this point xi by the retraction, and I would like to put some definable structure on this. And how do we do it? Actually, we use something in Berkovich geometry that's the very useful. It's what we call the residue curve. So let me introduce it in just a word. So one thing I didn't say in this picture is that, of course, you have additional structure. For instance, you have the point, say, xi. It is the generic point of a curve. So from it, you can basically recover the curve. And you can say what is the precise relation between this curve and the picture on the right. And you have a very precise relation in the following sense. So if you consider the completed residue field at the point xi, the residue field of this one, it is the same thing as the residue field of the generic point that is your reduction. And this is also the function field of a well-defined, smooth, projective curve over the residue field, okay? Which is something, not exactly the curve on the left, but it's normalization, basically. And this tells us something interesting because we have a bijection from the set of branches at the point xi. So I didn't say what branches are, but from this picture there, you see that you have some kind of a graph structure on your Berkovich space, and branches is just like the direction, some kind of tangent space, if you want, out of the point xi. Okay. And you have bijection between the set of branches at xi and the chaotic rational points of the curve ci. Okay. This is not so weird. Let me do it precisely on an example, like basically the one example we understand the best, the one of the affine line or the projective line. So projective line. X is P1 and say my point X is just the Gauss point. What would be the branches at the Gauss point, the set of branches? So you look at the point that's in the middle of your Berkovich space and all the direction out of it. It's just all the open disks, all the just the set of open unit disks. This point is precisely at the boundary of all the open unit disks you can find in your space. And an open unit disk, you can associate it in a well-defined way, a k point of P1. Okay, of course, yeah, like the center is not well-defined, but it's well-defined modulo the maximal ideal of your field. And so this map is actually something like the residue map. Mm-hmm. Okay. No. Ah. Okay, and so if you understood what I just did for P1, the thing is that this generalizes for arbitrary curves. So for general X, a general curve X, you still have this bijection. And you could do it also in some definable way. So this curve Ci, you can embed a closed embedding into some projective space over the residue field with some function, say f1, f1 twiddle, and then you lift each fi twiddle to bj to an element fj in curly h of x. You can do that since so this is this fi twiddle is a map from Ci to P1, which corresponds to rational function on P1, and this is precisely the residue field of curly h of xi. So you lift here, and actually the function field of your curve is already dense in that, so you can lift, or so better, you lift to a function fj in k of x in your curve, which is the same thing as a map from your curve to P1, which is automatically algebraic. And if you lift this correctly, so outcome is that you have reduction map that is defined on your curve, basically from x to the corresponding branch, or at least in the set Wx. Outcome. So from your set Wx to the branch, to the corresponding open disk, and which is the composition of the usual residue map, the one from P1, composed with F1 to Fr. Which means that this is something definable. So you have finitely many just algebraic functions, and the residue map, just take the usual residue class, and this looks like the residue map on your Berkovich space. Okay. Time to finish, but using this, I will just tell you now how we can define, give a definition of this set Wx. So now you pick a map or a morphism from from x to so from x to P1 that restricts to some map that sends Wx to the closed disk of center 0 radius 1. So this you can find, and you can find with very nice properties. This is not a problem. Morphism F. And how do you define this Wx? You just look at a map like this from Wx. So you go from the residue curve, or the Ketwidal point of the residue curves, times the disk. And you send a point y here to first the corresponding branch, the branch of the point y at x, and then the point of the disk you get by the map f. So it means that you just basically see this Wx as a cover of this disk, but you keep in mind which branch you were in the initial curve. And this is, if you do this properly, this is injective. Okay. And the image is definable. Okay. And so definable with, you need the residue field sort, and so to speak, the balls sort to take care of the disk here. And here you want the residue field. This is just an algebraic curve over the residue field, so you're safe. This is definable. So now we have, this is how we get the definability of our curve from writing this finitely many annuli and grouping those together around the point of the skeleton. This gives you a definition of the curve. And okay, so this is somehow a more concrete way to get it. And just let me state finally one theorem. This is that actually, if you think about it, we didn't do much here. We just take a set and say we can put a definable structure on it. So, okay, sure. And certainly many of them. But the thing is that the construction is functorial. And here we use work of Temkin to show that. But so if you associate to a triangulation a definable set, and if you have a map between two curves, the associated map would be a definable map. And also, since this is precise enough, we can get a very precise description of the definable sets in this setting. And final thing I would like to point out is that, of course, this definable structure here depends very much on the triangle. I mean, we use a triangulation to define it. If we chose another triangulation, we would find a definable bijection between the other one. And like the only thing that is actually canonical is when you take all the triangulation up to refinement. And so this is reminiscent of the fact that we have a pro-definable set when you take the limit over all possible triangulation of the set. And each of them gives the same definable set, but the only canonical thing is just the limit of all of them. And I will end up here. Thank you.